Hi everyone, today we're going to talk about conditional probability. The conditional probability is the probability when extra information is already known. So you're going to be talking about multiple different events that are occurring, and at least one of the events is going to be known. Okay, so you know what's going to happen. Real life rarely has just simple probabilities. An example would be the probability of a sports team winning state would be higher if you knew that the coach is also a former state champion. So if you're trying to find the probability of a sporting team winning state, well, you might want to know some other pieces of information, like if the coach was a former state champion. If that information is known, it's going to affect the probability of your sporting team winning state. So we're talking about conditional probability today. Situations like this where knowing one thing affects the total probability of some other event happening. So we need to talk about the notation for conditional probability. There's a couple new symbols that we need to discuss. In the past, we've talked about how the probability of an event can be written like this, almost like a function f of x. Well, the probability of an event given some other event happening is the probability of event B given, so like a bar, event A happening. So this little bar right here, this means given. And this event A, so we have two events, event B and event A. Event A, because it's after the given bar, it's given that this event has a certain outcome. So this is the known piece of information here. And so because this is new notation, we want to make sure that we understand how to say it. So when you read this out loud, you read it as the probability of event B given event A. Now, obviously, you're not going to call your events B and A. You're going to call them what they actually are, but that's how you would read it out. Now, the way to find conditional probability, there's a formula that goes along with this. And this formula looks like this. So the probability of this, and this little thing right here, this looks like an upside down horseshoe or an upside down U. You want to go ahead and write that. That's a new piece of terminology that we're going to discuss today. So the probability of B and A divided by the probability of A, the known event. This thing right here, this upside down U or this upside down horseshoe, whatever you want to call it, it means the intersection. The intersection of things happening. So it means one thing happens and the other thing is happening too. For example, if you're driving down Fairmont Parkway and you want to go to, I don't know, McDonald's or something. So if you're driving down Fairmont Parkway and you're going to McDonald's, which is on the corner of Fairmont Parkway and Preston. So as you're driving down Fairmont, as you get into the intersection, not only are you driving on Fairmont Parkway, but you are also driving on Preston. So the intersection is where you are on both. You are on Preston and Fairmont. So that's the and. So intersection means and. So the steps to solve is following the formula. You want to find the probability of event A, the known event. You also want to find the intersection of event A and B occurring. So the probability of B and A, that intersection. And then you want to divide that probability found in step 2, that intersection, you want to divide it by the probability found in step 1, which is the probability of the known event. So intersection divided by probability of known event. This is the formula. So if you were going to memorize one thing from the notes today, this would be it. These steps will work every single time, but sometimes thinking through the problem graphically or tabularly, so like in a table, is much easier than following the steps. We're going to practice both in each of our problems. So I'm going to refer back to this because I'm going to need the formula for conditional probability, and we're going to need to revisit the notation and what it means. So I'm going to kind of set this to the side. You'll be able to scroll up. And I go to example 1, and it says find the probability of rolling a dice and its value being less than 4, knowing that the value is an odd number. So those are our two events, the value being less than 4 and the value being an odd number. Now we're talking about rolling a die, and it doesn't say how many sides, so we are going to assume that it's a typical die with 6 sides and it's fair, meaning one side isn't weighted any more than the other. So we're not cheating here. So the sides of the die are 1, 2, 3, 4, 5, 6. Those are the typical sides of a die. And what I'm trying to find is the value or the probability of the value being less than 4, knowing that or given that the value is an odd number. So I need the probability of the value being less than 4, knowing that or given that the value is an odd number. This is what I need to find. And it's important to make sure that your events are in the correct order. Whatever is known or given, that goes at the end. So my steps say find the probability of event A, the known event. So that's the knowing that the value is odd. So I need to find the probability of picking an odd, of rolling a die and it landing on an odd number. So here are my choices. The odd numbers are 1 and 3 and 5. So that's 3 possible odd numbers out of 6 total possibilities that the die could land on. So 3 out of 6 simplifies to 1/2. That's the probability of the known event occurring. Now, step 2 says find the intersection of event A and event B occurring. So I need the probability that your number that you roll is less than 4 and odd. So I need to look at the numbers that are less than 4, so I'm ignoring 4, 5, and 6. And of those numbers that are less than 4, I need to know how many are odd. Well, 1 and 3 are odd, so that's 2 possible odd numbers less than 4 out of 6 possibilities to roll the die. So that's 1 out of 3. Step 3 is to divide the probability found in step 2 by the probability found in step 1. So the formula says that I need to find the probability of the intersection of the events divided by the probability of the known event. So the intersection probability was 1/3. The known event probability was 1/2. When we divide fractions, we keep the first fraction, and instead of dividing by the second fraction, we multiply by the reciprocal of the second fraction. So this is 2/3. That is the probability of rolling a die and its value being less than 4, knowing that the value is an odd number. Now, this is the way that you follow the formula. If I had not followed the formula, I could use something like a Venn diagram. My two events were the value being less than 4 and the value being an odd number. The numbers that are less than 4 are 1, 2, and 3. The values that are odd are 1, 3, and 5. In a Venn diagram, you want to put all of the pieces that belong with that title in the circle. Same thing here. All of the pieces that belong with this title go in this circle. However, the part that's in the middle is the part that overlaps. That part that overlaps is the numbers that are both less than 4 and odd. So I see that 1 is in both lists and 3 is in both lists. So 1 and 3 belong in that overlapping area. The numbers less than 4 that are not 1 and 3 is 2. So 2 goes in that circle as well. It's just not also an odd number. And then same thing here. 1 and 3 are odd, but 5 is also odd. It's just not also less than 4. So 5 belongs in the Venn diagram, but it doesn't belong in the middle. So if I'm trying to figure out the probability of rolling a die and its value being less than 4, knowing that the value is an odd number, well then I just ignore all of this. I only look at the odd number circle, and the probability that we roll a number less than 4, given that it's in this circle, is 2 out of 3. And that's our probability. So let's move on to example 2. We're going to do it with the formula, and then we'll do it with the Venn diagram. Now, I realize that in number 2, if you pause it and you read it, it talks about students and seniors and taking advanced math courses. It does not say how many total students are in the school. You can calculate an idea based on the information that they give you. However, what you calculate ends up kind of implying that any student that is not a senior is taking advanced math courses. And so I'd like to not imply that. I'm going to go ahead and add in that the total students are 500 in the school. So total of 500 students. So not all of the students are going to be in our Venn diagram. Sometimes you have a little rectangle outside, and the entire probability is contained in this Venn diagram, but it's important to know that everything all together will be 500 students. So in a school, there are 125 seniors and 200 students taking advanced math courses. 75 students are seniors taking an advanced math course. Given that a randomly chosen student is in advanced math, given that they are in advanced math, what is the probability that they are also a senior? So we need to reorganize this so that we're finding the probability of something given something else. So read the last sentence. What is it that is given? What event is given? The fact that they're in advanced math or the fact that they're a senior? It says given that the randomly chosen student is in advanced math. That is what is given. So that belongs at the end of this conditional probability statement. And we're going to abbreviate that to ADV, advanced math. So given that the chosen student is in advanced math, what is the probability that they are also a senior? That is the unknown probability. So my steps to solve say find the probability of event A, the known event. So I need the probability that a student is in advanced math. Well, how many students are in advanced math? There's 125 seniors, 200 students taking advanced math courses. There we go. That's it. So the number of students in advanced math is 200 out of the total number of students, which I told you before was 500. So 200 over 500 simplifies to 2/5. Now step 2 says find the intersection of events A and B occurring. So both events occurring at the same time. I need the probability that the student is a senior and in advanced math. So I go find the number of students who are seniors who are taking advanced math. There's 125 seniors, 200 students in advanced math, 75 students are seniors taking advanced math. So the 75 is the number that is both seniors and advanced math students. So 75 out of the total, which is 500. Both of these can be simplified by 25. Think about money and quarters. So 75 divided by 25 is 3. And 500 divided by 25 is, what is that, 20. So now I need to calculate the probability that your student is a senior given that they are in advanced math courses. So I need the probability of the intersection, that they're a senior and in advanced math, divided by the probability that they're in advanced math. So that's 3 out of 20, divided by 2 out of 5, 3 out of 20 times the reciprocal, 5 over 2. The 5 and the 20 are both simplifiable by 5. So this is 3 out of 8. The probability that a student chosen at random is a senior, given that they're in an advanced math class, is 3 out of 8. Now, if I didn't use the formula and I just used the Venn diagram, my two events were that the student was a senior and the student was in advanced math. Now, the number of seniors, there were 125. The number of advanced math students, there were 200. There's a lot of students that were not seniors or in advanced math. They're kind of floating out here, and we're not really worrying about those right now. We did have 75 students that overlap, that they were seniors and taking advanced math courses, so I would put those in the middle. Now, in my Venn diagram, if I cover up this part, the number of students who were seniors was 125. If 75 of those belong in the middle, how would you figure out how many go over here in the rest of the Venn diagram? If you thought subtraction, you would be correct. 125 minus the 75 who are taking advanced math leaves 50 students who are seniors but not in advanced math classes. Same idea with the other circle. If you have 200 students taking advanced math, 75 of them are seniors, the other amount are not seniors. How many are not seniors? So 200 minus 75 would give you 125. If I were trying to find the probability that a student was a senior, given that they're in an advanced math class, I'd only look at the advanced math class in the Venn diagram, and the probability that they are a senior out of this is 75 out of 125. Or sorry, 75 out of the sum of these, which is 200. So if you simplify 75 out of 200 by 25, you get 3 out of 8, which is what we got using our formula. Okay, so with a Venn diagram, it's relatively easy as long as you put your pieces in the right place for your Venn diagram. If you make a mistake and you put the wrong numbers in the wrong places, things get messy. However, the formula will always work. In example 3, it says, in a class of students, the following data table summarizes the gender of the students, whether they have an A in the class. What is the probability that a student has an A given that they are male? So we are only considering the possibilities of male and female here. I want the probability that a student has an A given that they are male. So what is the probability? What is the event that is given, that is guaranteed? Is it the student has an A or the student is male? Given they are male. So I need the probability of a student having an A given that they are male. So I need to find the known probability, the probability of a male student. So I go look at my table. I've got females here and males here. So the number of males is 8 plus 5. And 8 plus 5 is 13. So that's 13 out of the number of total students. And the number of total students is 13 plus 14, and 13 plus 14 is 27. So that's 13 out of 27, not simplifiable. Now step 2 is to find the intersection, so the probability that your student is male and earning an A in the course. So here's the number of male students, here's the number of students that have an A in the course. The numbers that overlap is this one right here. And so that's 8 students out of 27 students. So the probability that we have a student with an A given that they are male is the intersection divided by the known probability. So that's 8 out of 27 divided by 13 out of 27. That's 8 out of 27 times the reciprocal of 27 over 13. The 27s cancel. Our probability is 8 out of 13. So the probability that a student has an A given that they are a male in this class is 8 out of 13. If I ignore the fact that I did this, and I just look at the table, and I want the probability that the student has an A given that they are male, well, that means that I'm only looking in the column with male students. And if I want the probability that they have an A, that's 8 students out of this total here, which is 13. It's the same number that we got here. All right, let's turn the page. Example 4. In a class of students, the following data summarizes how many students passed a test and completed the homework due the day of the test. What is the probability that the student passed the test given that they did complete the homework? Those are our two events. What was given? What is known? Is it that the student passed the test or that they completed the homework? It is given that they completed the homework. So I need the probability that they pass given that they did the homework. So step 1, I find the known probability that they did the homework. So the number of students that completed the homework, that's right here. 18 plus 2, that's 20. Out of the total number of students, so 20 plus 5 is 25, plus 9 is 34. So total is 34. So 20 out of 34 did the homework. That simplifies to 10 over 17. Step 2 is to find the intersection, the probability that the student passed and did the homework. So the students who were in this column and this row would be 18. Out of all the students, 34. That simplifies to 9 out of 17. So the probability that a student passed, given that they completed the homework, is the intersection divided by the known probability. That's 9 out of 17 divided by 10 out of 17. That's 9 out of 17 times 17 over 10. The 17s will cancel, and we're left with 9 out of 10. This is the probability that a student passed the test given that they completed the homework. If you ignored our work and you just looked at the table, and I want the probability that a student passed the test given that they completed the homework, I'm only looking at the completed homework row. The students who passed are 18 out of 20 that completed the homework, and 18 out of 20 simplifies to 9 out of 10. Okay. We're going to skip example 5. We'll come back to it. I want you to look at example 6. It talks about pets, cats, and dogs. This says car or dog. That is wrong. Go ahead and cross it out. Put cat. I want you to pause your video and try example 6. Try to calculate the conditional probability that a student who has a cat also has a dog. Make sure that you understand what the given event is, whether it's having a cat or having a dog. So take a moment, pause your video, and try example 6. So question 6 says, in a class of students, the following data summarizes how many students have a cat or dog. What is the probability that a student who has a cat also has a dog? Now, there's no language in here about given something or we know that something is happening. There's no information about that. So we need to figure out what is known. Is it known that the student has a cat or that the student has a dog? It says, what is the probability that a student who has a cat, the student has a cat. We want to know the probability about this student who has a cat and if they also have a dog. So the known piece of information is that the student has a cat. So we want to know the probability of dog given cat. Step 1 is to find the known probability of having a cat. So that's this column right here. That's 9 students out of a total of 21. That simplifies to 3/7. The probability of the intersection of dog and cat. So here's the cats, here's the dogs. The number that's a cat and dog student is 3. So there are 3 students out of 21 that have both. That's 1 out of 7. So the probability that a student has a dog given that they have a cat is the intersection over the probability of the known event. So that's 1 over 7 divided by 3 over 7, or 1 over 7 times 7/3. The 7's cancel, and you're left with a probability of 1/3. Now, if you didn't use the formula and you just used the table, the probability that a student who has a cat also has a dog, we're looking at only the cat column because the student has a cat. And of those, the students that have dogs are 3 out of 9 total cat owners. So 3 out of 9 simplifies to 1 over 3. Last problem, example 5. Pause your video and try it out. In example 5, we want the probability that a student has a sister given that they have a brother. So there's a total, if I add all of these up, of 22 students. I want the probability that the student has a sister given that they have a brother. So I want the known probability of having the brother. The students that have a brother are 13 out of 22, so there's my probability. Now I find the intersection, the students who have a sister and a brother. So of the ones that have a brother, the ones that also have a sister is 8 out of 22. So here we go. If I find the probability of having a sister given that they have a brother, I want the intersection here over the known probability here. That's 8 over 22 times the reciprocal, 22 over 13. The 22's cancel. So the conditional probability is 8 out of 13. If I ignore the formula and I just look at the table, the probability that a student has a sister given that they have a brother would be in this column, so has brother column. And if they have a brother, the ones who also have a sister is 8 out of the other ones that have a brother, which is 13. So 8 out of 13 would be that conditional probability from the table.